Welcome to Rate Law and Order, example number 2. Again, you are going to need your calculator, you are going to need paper, and you're going to need a pen or pencil. Please take notes on questions as we go along, or take notes with information that's critical that I point out as we go along. And if the questions you have are not answered in this lecture, then please make sure that you post those questions to your teacher's office hours discussion board, because your posting will again be beneficial to everyone in the class with your teacher's answer. Let's start. Here we have another data table. In this data table, again, we have 3 independent experiments. Remember, independent experiments mean that none of the other experiments are dependent upon what's happened in another experiment. So we're just looking at data. We want to find the concentration for reactant A changing, but we want the concentration for reactant B not changing. So take a moment and see if you can figure out which 2 experiments should we actually look at. Please feel free to pause the video if you need to and press play when you're ready. To figure out the order of reactant A, we are going to look at experiment 2 and experiment 3. In experiment 2 and experiment 3, we find that the concentration of reactant A is going to double. We find that the concentration of reactant B is staying the same. And that allows us to look at the rate of reaction for the 2 experiments. Well, when we look at that rate of reaction, we find that when concentration of reactant A is 0.25 molar, the rate change is at 2.86 e to the negative 6 molar per second. We find that if we double, and I'm going to put a little 2 here for A, if we double the concentration of reactant A, we find that the rate changes to 1.144 e to the negative 5. Of the 2 rates, 144 e to the negative 5 is a higher rate. So we just want to find out how that factor changes from the rate it was. So we're going to divide, make sure I can write this right, 1.144 e to the negative 5 by 2.86 e to the negative 6. Now, it might occur to someone why we're using a lower number in our numerator. Well, to do that, you have to look at what the power is. Yes, 2.86 is a higher number than 1.144. However, that 2.86 is to a negative 6. The 1.144 is to a negative 5. The 1.144 is a higher number because its exponent is higher at a negative 5 than at a negative 6. If you have a question and you're not comfortable with that, my recommendation is that you contact your math teacher. Explain to her that we are doing rate laws. Show her the 2 numbers and have her explain to you the difference between the 2. So clear your calculator. Put in 1.144 e negative 5. Remember, if you're going to use your times 10 key, you have to put it in parentheses. In other words, you'd have an open parentheses, 1.144 times 10 to the negative 5, close parentheses, so that your calculator knows that's one thing, or that's one expression for you. And you're going to divide this by either 2.86 e negative 6 or open parentheses, 2.86 times 10 to the negative 6, close parentheses. Push the equal button, and you should come up with an answer that is either close to or can be rounded to 4. All right? 2 to what power is equal to 4? 2 to the second power is equal to 4. So that takes care of reactant A. Now let's look at reactant B. If you need to, pause this video. Do these manipulations again to make sure you understand them. Write down if you have a question that you're not sure of, so that we can see if we solve that as we go through this lecture. Or you can post that in your teacher's office hours discussion board. Now we're going to look at reactant B. Can you figure out which two experiments we would use for reactant B? If you need to, pause this video, see if you can't figure that out, and then play the video to see if you got it correct. For reactant B, we are going to look at experiment 1 and experiment 2. Why are we looking at experiment 1 and experiment 2? Because we find that in experiment 1 and experiment 2, reactant A, let me do it this way. There we go. Reactant A stays the same, but reactant B is going to double, and that now allows us to look at what happens to the rate of the reaction. So, reactant A stays the same, reactant B doubles, and when we look at the rate of the reaction, in experiment 1, the rate is 1.43 e to the negative 6. In experiment 2, the rate is 2.86 e to the negative 6. Of these two rates, the 2.86 e to the negative 6 is the faster of the two. Why? Because your powers are both to a negative 6. So 2.86 is your larger number. So 2.86 e to the negative 6 divided by 1.43 e to the negative 6. Clear your calculator. Put in 2.86 e negative 6 divided by 1.43 e negative 6 if you're going to use the e key. If you are not going to use the e key, then you're going to have to put in open parentheses 2.86 times 10 to the negative 6 close parentheses divided by open parentheses 1.43 times 10 to the negative 6 close parentheses. Press your equal sign, and you should get a number that either can round up to or is equal to the number 2. 2 to what power is equal to the number 2? 2 to the first power is equal to the number 2. I think I went over when we did example 1 that any base number to the 0 power is going to be equal to 1. Any base number to the power of 1 will be equal to whatever that base number is. Well, since 2 is what happens to your rate of reaction, or it doubles, and you've doubled your reactant, then your power is going to be a 1. Okay? That's one way to do it. Remember, we showed you a different way of doing it where you do the divisions. Well, in the division, looking for concentration A, we still use experiment 2 and experiment 3. However, when we look at our rate of reaction, since the doubling of A causes your rate to change to 1.144 times 10 to the negative 5 in experiment 3, and leaving your reactant A at 0.25, not no changing of your reactant B, gives you a initial rate or rate of reaction of 2.86 e to the negative 6. Of those two, the 1.144 being the highest rate, we are going to put experiment 3 in the numerator and experiment 2 in the denominator. Because again, while experiment 2 has a number of 2.86 and experiment 3 has a number of 1.144, experiment 2 is to the power of negative 6 and experiment 3 is to the power of negative 5. So it's a larger number. Then we just cancel out your constants, cancel out the concentration B. We find that 1.144 e to the negative 5 divided by 2.86 e to the negative 6 is going to be equal to 4. We find that 0.5 divided by 0.25 is going to be equal to 2 to the x power, and 2 to the power of 2 is equal to 4. So x is equal to 2. If we look at concentration B, once again, we're still going to use experiment 1 and experiment number 2. However, because of the rates of the reaction, we find that in experiment 1, when B is 0.250, your rate is 1.43 e to the negative 6. But when you double reactant B, leaving reactant A the same, your rate changes to 2.86 e to the negative 6. Of those two rates, the 2.86 is the larger because it's the larger number and your powers are the same. So we choose the larger number. So your experiment 2 becomes the numerator is on top, and experiment 1 is the denominator or is at the bottom. And then we cancel our constants. We cancel reactant A. And when we look at 2.86 e to the negative 6 and divide that by 1.42 e to the negative 6, we find that that is a rate change of 2, or a number that can be rounded to 2. And when we take 0.500 and divide that by 0.250 for the concentration of reactant B, we find that it has doubled to the y power. And then, of course, 2 to what power is equal to 2? 2 to the first power, or power of 1, is equal to 2. All right? I would suggest that you pause the video before we go into this part. Go back and do those two problems. Make sure you're comfortable with how that problem is done and you understand what we did in those problems. Write the questions down if you still have them, or eliminate the question you had if we've answered them. But if you still have questions, those are the questions that hopefully will be answered before we finish this lecture, or you'll be able to post for your teacher on their discussion board office hours. Okay? Play the video when you're ready to move on. So now we know that concentration A, reactant A, is to the power of 2, or the second order. We know that reactant B is to the power of 1, or to the first order. Now what we want to do is we want to plug them into our, I'm just going to call it a skeleton of the rate law. When we plug it into that rate law, we find that we get the rate is equal to the constant of the concentration of A to the second power times the concentration of B to the first power. Pause the video, make sure you understand what we've done, make sure you understand why it looks the way it looks, why we plug those into the rate law expression, and press play when you're ready. That being done, we are going to look at the exponents of our rate law. A is to the second power, B is to the first power. That gives us our overall rate, which is going to be equal to 2 plus 1, which is 3. So our overall order, of the reaction is 2 plus 1, which equals 3. Pause the video, make sure you understand why. Check your questions, see if we answered them, or write more questions if you have them. Press play when you're ready to move on. Now we're looking at the 3 most common cases. What do we mean? Well, usually we double reactions. Sometimes we'll triple them, but usually we'll double the concentration of one reactant. And then we look at what effect it has on the reaction rate. We find that if the concentration doubles of the reactant and the rate stays the same, then we just automatically use the exponent 0, because any number to the 0 power is equal to 1. So if you double to the 0 power, it equals 1. 1 means the rate stayed the same, because if you divide the rates by each other, you're going to get the number 1. If, however, the concentration doubles and the rate doubles, well, we change the exponent from 0 to 1, because 2 to the 1 power is equal to 2. Again, any number to the 1 power is going to be equal to the number itself. And of course, if the concentration doubles and the rate quadruples, well, then we use the exponent 2, because 2 to the second power is equal to the 4. Is it only doubling? No, sometimes we can actually triple the concentration. And if I triple the concentration but nothing changes in the rate between the 2 experiments, then it's going to be 3 to the 0 power, which is equal to 1. If I triple the concentration of that reactant and my rate triples, then it would be 3 to the first power, because that's equal to 3. And if I triple my concentration and I find that the rate change is a factor of 9, then it would be 3 to the second power, because 3 to the second power is equal to 9. If I were you, I would probably make my recommendation to write that down and just kind of put a notation on it that you need to know that. Okay? So, here we have an actual equation. F2, the gas, plus 2ClO2, the gas, produces 2FClO2, the gas. We are going to look at the reactants, F2 and ClO2. We are going to determine the order of both reactants. We are going to put them in the rate law expression, and we are going to determine the overall order. This is your practice. So I'm going to let you practice it. I'm going to put it up. You see if you can solve it, and pause the video. And when you're ready to check your answer, press play. This is what I'll just call this the skeleton of the format you're going to use to write your rate law. You're going to put the order of F2 here and the order of CL2 there in order to write your rate law expression. So, here's your chart. What do you have to do? You need to determine which 2 experiments you're going to use to find the order of F2, which 2 experiments you're going to use to find the order of ClO2. Write the rate law expression, and then give me the overall order of the reaction. Remember, when you're doing this, there are 2 things you want to do. You want one of the reactants to stay the same. You want the other, the reactant, to change. Those are the 2 experiments that you're looking for, where one of the reactants stays the same, the other reactant changes. When you're looking at your rates, you want to know what rate, by what factor that rate is changing. So you're going to divide the larger number or the faster rate over the smaller number. And then based on whatever that change is to whatever power, it's going to be equal to whatever number you got by dividing the larger number over the smaller number for your rate. So good luck. Pause the video at this time, do the problem, and then come back when you're ready. Press play. Okay, so for this one, the two better experiments that I would say would be to use, and where I want to double, would be to use experiment 1 for fluorine and experiment 3 for fluorine. Well, why am I using that? Well, in experiment 1 and experiment 3, notice that the ClO2 stays the same, but in experiment 1, fluorine is 0.1, F2 is 0.1, and fluorine gas is 0.2. So that's a doubling. That's cool. That's easy enough. And then when I look over here to my reaction rates, I find that in experiment 1, the rate is 1.2 e to the negative 3. Experiment 3, the rate is 2.4 e to the negative 3. So I take 2.4 e negative 3, and I'm going to divide that by 1.2 e negative 3. And the number I get should be equal to, or can be rounded to, the number 2. And like we said before, any number to the first power is going to be equal to itself. So that's 2 to the 1. Pause your video if you need to double check, especially if you got it incorrect. If you got it correct, just keep on. Press play when you're ready. So then, when I look at my ClO2, I'm trying to leave my F2 constant. So for that one, I'm going to use experiment 1 and experiment 2. Because in experiment 1, the F2 stays the same, but my ClO2 is going to change. At first, it's 0.01, and then it's 0.02, which again is a doubling. Works out great. And when I look at my rate of reaction, I see that there is no change. So when I divide them by each other, 1.2 e to the 3 divided by 1.2 e to the negative 3, it is going to be equal to 1. And once again, any number to its power of 0 is going to be equal to 1. So that takes care of reactant A, F2, and reactant ClO2. Again, pause the video if you need to. Go through what I just did. Make sure you understand it, or answer your question, or write a new question. If you got that correct, go ahead and on with the video. Otherwise, pause it and then press play when you're ready. Okay, so now I am ready to write my reaction rate. Since I know that F2 is of the first order, I know that ClO2 is of the 0 order, I'm just going to plug those into the powers on my rate law expression, and that is going to give me that rate is equal to constant F2 to the first power, ClO2 to the 0 power. And I also now know that my overall order for my reaction is going to be equal to 1. Pause the video if you need to. Otherwise, keep going. Press play when you're ready. So for practice number 2, this time, I have 2H2 the gas plus O2 the gas produces 2H2O the liquid. This is my rate expression I need to fill in for X and Y. And here is my chart. At this point, pause the video. Make sure that you have your calculator, pencil, paper, and see if you can't solve this problem. We need to find the order of H2. We need to find the order of O2. We need to write the rate law expression correctly, and we need to find the overall order of the reaction. Pause your video, play when you're ready to check your answers. In this one, we are going to double H2 and we want O2 constant. So I'm going to use, let me see if I can find me another color. There we go, blue is cool. I'm going to use the experiment of 1 and 3 because in 1 and 3 my O2 doesn't change, but my H2 goes from 0.150 to 0.300, which is a doubling. And my rate is at 1.2 e to the negative 3 in experiment 1 and 1.2 e to the negative 3 in experiment 3. And if I just want to check myself, and I put in 1.2 e to the negative 3 divided by 1.2 e to the negative 3, so negative, not an equal sign. Got a little excited, I guess. That is going to be equal to 1. And so now I know that 2 to the 0 power is going to be equal to 1. If I look at the O2, this time I want to double my O2. Well, my O2 is doubling rather. But I want my H2 to stay constant. For that, I'm going to use experiment 1, and I'm going to use experiment 2. Because in experiment 1 and 2, my hydrogen stays the same. And in experiment 1, I have 0.15 of oxygen. Experiment 2, I have 0.3, which means there is a doubling. And then when I look at my rates, my rate is going from, in experiment, well, not from, but in experiment 1 is 1.2 e to the negative 3, and in experiment 2 it is 4.8 e to the negative 3. So that's a difference. So I need to find out what factor is changing, or by what factor it's changing. So I'm going to take 4.8 e to the negative 3. I'm going to divide that by 1.2 e to the negative 3. Do the math. And I should come up with a number that can be rounded to or is equal to 4. And 2 to the second power is equal to 4. If you got that correct, you're doing fine. If you didn't get it correct, make sure you write what question you have so you can post it on your teacher's discussion board for their office hours. Okay? Having done that, I now know that H2 is to the 0 order and O2 is to the second order. My rate law expression is rate is equal to the constant H2 to the 0 power, O2 to the 2 power, and I now know that my overall is just adding that 0 and adding that 2 together, which gives me my overall order of the reaction, which is equal to 2. This concludes your section on rate law and order, example 2. My recommendation is that you go back through this video, work those problems, Because practice, I'm going to write that down. Practice. Because that's just my favorite expression. And those of you who know Dr. Hudson, you know that's my favorite expression. Practice. 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 Can you say with me what practice makes? Perfect. Practice makes perfect.